Right, welcome back. This is CX1104. So this is CX1104. Today we'll do tutorial 6, question number 12 about QR decomposition. And before I do that, then I would just review Gram-Schmidt for QR first. So we are given a matrix rectangle, n by n, and we are going to decompose into a product of two matrices, Q and R. So Q times R equals to A. That's called matrix decomposition. There are many decomposition. QR is one of them. And the properties of Q is this. The column space of Q will span the column space of A. QTQ would be octonormal. QQT is a projection matrix of the column space of A. R is upper triangle. So these are all the properties that we need from the QR decomposition. And you'll be thinking, why would we want to do that? And QR decomposition has a lot of use. Finding the solution is one of them, of X. So later on, you have AX equals to Y. Substitute A as QR, X equals to Y. And because Q is orthogonal and or has octonormal columns, then we can do many tricks with it. When you see that this theorem only deals with linearly independent column, means that this is a special case. Okay, sometimes A don't have linearly independent columns, then this cannot be used. But when it has, then yes, this theorem applies. All right, so how does it look like? So A is, for example, let's try this, a 4x3 matrix. And then let's say A has linearly independent column, meaning all these blue guys here are linearly independent. And then Q will be also 4x3. And of course, to get the correct size, R must be 3x3. So 4x3, 3x3 will give us a 4x3 matrix. Now, what's so special about Q is that all these guys, they are not the same as these guys on the left of in the A, but they span the same space. Not only they span the same space, they are octonormal columns, meaning that the norm, the length of each of these vectors, here, all these guys, the length of these vectors, they are, for example, let's call this Q1 for the length for the column of 1. The column 1 of Q1 is 1. Q2, same, 2. Equals to 1. And so on. So basically, all the columns have length 1. Not only they have length 1, they are orthogonal to each other. So Q is a very special matrix. And this lesson, in this tutorial, we're going to find out how we can generate Q and R. To understand why I want to do Q and R, remember Q has octonormal columns. What does octonormal means? Means it is orthogonal. The columns are orthogonal and their length equals to 1. So octonormal is a more strict version of orthogonal. Of course, if they are octonormal, they are also orthogonal. We say that Q, remember, spans the same column space as A. So if they span the same column space of A, they are also a basis. So we're going to use this theorem now with orthogonal basis. What does orthogonal basis do? Well, let's try this. Here is the abstract form. Let W be a subspace of Rn. So this is a vector. So it has 1, 2, and n. So this is Rn. This is a vector with n element. A subspace basically means, for example, I have A1 here. I have another A2 here, which is also Rn. And then I have a few more. Oh, okay, let's stop at 2 first. And then what is W? Let's say I say W is spanned by A1 and A2, and A1 is orthogonal to A2. So W is spanned by two vectors which are independent. Not only they are independent, they are orthogonal to each other. So how would it look like? So one guy will be pointing to here, which is called A1. The other guy, which is right angled to him, will be A2. And the green box is the span of A1 and A2. So this is how we can visualize what this green plane is. They are the span of these two independent vectors. We need A1 and A2 to be independent. We do not need A1 and A2 to be orthogonal, but they have to be independent. If they are orthogonal, like in this example, because I have said it here, then we can use this very nice equation to construct or to approximate y. Okay, let's try. Y is of course in Rn also. For example, a y is in R3, and we only have, in this example, I guess, now let's simplify it again. We only have until three elements. So A1 has 3 elements, A2 has 3 elements, and Y is 3 elements, R3. This Y can be broken down into two parts. One part, Y hat, that is in the space of W, and Z is orthogonal to W. So this picture is very nice. This, for example, A1 is the x-axis, as you're all. A2 is in the y-axis, for example, and in the z-axis, which is here, we don't have. So how would A1 and A2 look like? A1 might be 1, 0, 0, 0, 1, 0, and then that's it. So this is really a very simple example of what A1 and A2 will look like. It will only span 2 dimensions out of the 3 dimensions in R3. This is a plane. And now we want to get, we have Y. So maybe I'm going to have Y is maybe 3, 2, and maybe 4. So this is 3 here along the x-axis, 2 here along the y-axis, and here we have 4. So Y is definitely, not in the plane of W, because the plane of W is the horizontal plane spanned by these two guys. Now, the orthogonal decomposition is very nice. He says that if you have orthogonal basis here, then simply to calculate the weights associated with the orthogonal basis, you just need to do this equation. And this equation, as you all know now, is the projection of Y onto U1. This equation is the projection of Y onto UP. Okay, and the projection of Y onto U1, Y onto UP can be calculated independently of each other, U1, U2, U3. And the reason is because this is orthogonal basis. For the proof, please see the lecture notes. Once we have orthogonal basis, we realize that this equation is not so nice here in the bottom, because in the bottom you can see u1.u1 and up.up. Now imagine that the length of, if the length of u1 equals to 1, then u1.u1 is 1. So it reduces from orthogonal decomposition to something called octonormal basis, octonormal decomposition. So you'll see that there is nothing in below as compared to equation 2 here. So we prefer octonormal basis, and that's where Q comes in. A equals to QR. Q is a octonormal basis spanning the same column space of A. And then we have all these nice equations that we use. With that, I think we are ready to start the QR decomposition. Given A, we are going to generate Q. The number of columns in A is N. the number of columns in Q is n. All these columns spans the same space as here. Not only that, the columns of Q are octonormal. Right, we'll now begin to answer tutorial 6, question 12, part 2. The question asks us to find the QR decomposition, or sometimes called the factorization. These are interchangeable. We're given a matrix of 4 by 3 columns, and let us call the columns x1, x2, and x3. A's column are linearly independent because immediately it is obvious that the second column cannot be constructed by the first column. The third column cannot be constructed by the first 2 columns. So, but they are not orthogonal. x1 dot x2 is not equals to 0. They are not octonormal. The length of x1 is not 1. We want to find Q such that the columns of Q spans the same space as A. How do we do that? Now we're going to do QR decomposition. There are 2 types of QR decomposition. Here we'll do the economy, as in the smaller versions of the QR. Q comes out to be 4 by 3. If I have a 4 by 3 A, Q will be 4 by 3. A full QR will generate a 4 by 4. So you must be very careful. So this is an economy factorization. Now you can see all these examples here, and there's a reference. The equation, the brute force thing that you need to remember is how are we going to generate QR first. To generate QR, first, A will be changed to a matrix called V. V will be changed to a matrix called Q. So we are going to do the step V now. V will be generating a set of vectors that is orthogonal to each other and span the same space of A. So it hasn't been octonormal yet. The first one is very easy. V gets a copy of x1. So V1 is x1. That's it. If I only get one copy of x1, I have solved the first column's problem, but I haven't solved the second and third column. Okay, remember in our question, we have 3 columns. So all we did was to copy this and we copy into V1. That's it. Now what about the second guy? What about the third guy? So how do I go to V2? V2 is x2, the input. So now I'm going to use green. This column is going to be used and subtracted with this thing. What is this thing? This is the projection of x2 onto V1. Remember who's V1? V1 is here. In English, what does it mean? It means that I am using, to get my V2, I'm using the input x2 and I am subtracting it from what x2, how x2 will land on V1, and I get the residual. I should draw a diagram. Let me draw a diagram for you. If this is V1, this is x2, I am projecting this point, or this vector, I should say. This vector here is the projection of x2 onto V1. What about this vector? This vector is orthogonal. So I'm interested to get this vector and set this as V2. Because why? Now I have V1, I have V2, which are orthogonal to each other, spanning the space of x1 and x2. So this cool Gram-Schmidt process is doing this. I have gotten my V1. I now project my x2 onto V1, and I get the residual, and the residual will be orthogonal to V1. And I set it as V2. I repeat the process for V3 using projection of x3 onto V1, projecting x3 onto V2. If I subtract my contribution of x3 from V1 and V2, whatever I'm left with is the orthogonal part of it. All right, so I told you that there are 3 parts to this question. First, I go from A to V, which is an orthogonal set. I need an octonormal set. So all I do is I get Q is nothing but V1 divided by the norm of V1, V2 divided by norm of V2, V3 divided by norm of V3. And I get 3 column vectors that is belonging to R4. Each column is R4. These 3 column vectors are orthogonal and octonormal. So Q now is an octonormal set spanning the column space of A. I should say column space of A. All right, so this is the Gram-Schmidt process. The details are here. So let's try it now. Remember, V1 is the simplest one. It just copies X1. V2 takes the input X2 and minus, and if you forget this guy, it is nothing but the projection of X2 onto V1. If you forget how to do this equation, this is the equation up there. Let's identify this is V1. Projection of X2 onto V1 is a vector along V1 scaled by this value. So you go through the mechanics and we get V2. Now, we end up with this vector, and this vector is very hard to deal with because of the 4. Since we don't care about the length of V2, we only need to have the direction. Then we multiply everything by 4. So this guy multiplied by 4 is -3. This guy multiplied by 4 is 1. And then we get a vector with a whole number so that we can deal with it more easily later on. Now, compare and contrast this. Compare this equation here, which is V3, and this equation here. They are the same equation. The notation is slightly different. So X3 is here, so this is X3. The only difference is this guy. So you realize that this sum is projection of X3 onto W2. What is W2? It is the base. This W2 is the space spanned by V1 and V2. Right? You work through the math, and then we get the solution here, and we can calculate. So this is projection of X3 onto W2 means how would X3 look like in the space of W2? Where is the nearest point in W2 to X3? So this is the nearest point. And then this is when I take the X3 minus the nearest point, I am getting the error, the residual left, what is left. And I set it as V3. So I've gotten V1, V2, V3. So you go through the mechanics. And now to get Q, all I do was to divide each of these vector by its norm such that each of these length now is 1. Not only are they 1, you try to dot product between all these vectors, they are 0. So Q is an octonormal set. Now, I've solved for Q, but remember that A is equals to QR. Now, since Q has octonormal columns, Q transpose Q will be equals to the identity. Okay, so what you do is that you take this Q here, you make a transpose. So Q transpose will become, this is 4 by 3. So this will become 3 by 4. So this is 4 by 3. Q transpose Q is 3 by 4 multiplied by 4 by 3 equals to 3 by 3. Since all the columns are orthogonal, so only Q1 transpose Q1 has any value. Since each column is normal, Q1 transpose Q1 is 1. So that's why we get identity. So something interesting happened now. Remember, we multiply both sides by Q transpose. Q transpose A is Q transpose QR. Q transpose Q is I. I is identity. Identity times R is R. So Q transpose A gets R. We know Q, we know A, we can get Q transpose. So it is trivial to get R. So then by brute force, we compute Q transpose A, and this is R. If you got it wrong, you will not get the upper triangle matrix. If you make a mistake, then the columns of Q are not orthogonal to each other. they don't have length 1. So this is how you check. Finally, if you also want to check, remember that the column space of Q is the column space of A. So what does that mean? So you take Q and you take each of these A and you do what you call that, the Gaussian elimination. You are trying to use the columns of Q to approximate A. Since A is in the column space of Q, there is always a solution. So this is one way to verify that you did it correctly. The other way, which is even more interesting, you take Q and you multiply with Q transpose. So maybe you guys have not seen this yet. Let me have only a Q with one column. So let's say this is a 3 by 1 vector. So what about Q transpose? Q transpose equals to 1 by 3. What is Q transpose? It is 3 by 1, 1 by 3. What do I get? 3 by 3. So this is sometimes called the outer product. I take a column vector, I multiply by its transpose. I actually take a column vector, multiply its transpose. I get a square matrix. Let's try a very simple example. 1, 2, 3. Okay. 1, 2, 3. What do I get, guys? Try it by yourself. You'll get the first column is 1, 2, 3. The second one, it is nothing but this entry multiplied by this column vector. So this is 2, 4, 6. Over the third guy is the third entry multiplied by the column. It is 3, 6, 9. So you'll see that this is the original column. This is the second element times the original column. This is the third element times the original column. So all the columns are dependent on the first column. This is although this is a 3 by 3 matrix, this has only rank 1 because it has only one independent row or one independent column. Now, if you understand this concept, figure out Q times Q transpose. Q has a few columns, and Q transpose is that few columns transpose. It is also an outer product. So I have Q is 4 by 3, so I have 3 columns that are octonormal. I multiply with that 3 columns. And interestingly, I don't get identity, not identity, because I have only 3 independent columns. I generate a 4 by 4 matrix. This 4 by 4 matrix need 4 independent columns. I only have 3 independent columns. So this is a rank 3 matrix. It is not an identity. And P is something called a projection matrix. And it has a very important interpretation. P is a projection matrix that allows us to play with different inputs. And we will see how the input land in the column space of P, which is the same as column space of our original matrix A. P times each column of A, we get exactly what A is. It shows that P spans the same column space of A. Right. So with that, I pause here and I'll take questions now.